This is WK3.H. We're going to be looking at horizontal circles. In this example, we are going to be examining a police car. It's got mass M, moving at constant speed around a curve of radius R. So we have constant speed circular motion. The car in this picture is essentially coming out of the page. So somewhere over here is the center of the circle that it's traveling around, and that's the radius R, let's say, that is referenced. So the car is coming out of the page and kind of turning to your left as it comes out. So there's a maximum safe speed. So you should probably recognize this as a driver. If you are going around a curve, if you go too fast, your tires are not going to be able to hold you on that circular path. You're going to start skidding to the outside of the circle because your tires can't produce enough static friction to drive you towards the center of the circle. All right, so that's what's holding you, pulling you towards the center. So let's examine it. The dot at the right represents the car. Free body diagram showing the labeling of the forces as it rounds the corner. So obviously the road is touching it. That would we could call that the normal force. Up and down, there's no acceleration, so we want to make sure that that force is balanced appropriately with the force of the earth. So up and down, there is none. Over here, remember, is the center of the circle. So at that center of the circle, we need to draw that force that is radially acting to pull it towards the center. It might feel a little bit weird that friction is acting towards the center, but we know that if the car is moving in constant speed circular motion, the sum of the forces must be acting towards the center. The only force that's left that could be pointed that way, obviously, is that frictional force. So it's static friction, because as we discussed before, the tires aren't slipping. The tires, as they contact the surface, do not slip. So there is no relative motion between the tires and the road surface. So it's a form of static friction. There's no other forces that can be pulling it towards the center, so that has got to be the direction of that frictional force. All right, so we want to create an argument. We want to examine this. We want to understand it conceptually so that we can represent it, discuss it without necessarily pulling out our equations. So we know that friction, on the one hand, friction is going to, that frictional force, that static frictional force is going to be less than or equal to mu times n. Remember, it has a minimum value of 0, but it has a maximum value of mu times n, mu sub s. It can't get any bigger. And that's what happens when a car starts skidding to the outside of the turn, is we've reached that maximum static friction, and maybe that can be delivered. Otherwise, if we go slow enough, then we can provide enough static friction to move our car towards the center of the circle, accelerate it towards the center. So suppose the car encounters a wet section of a curved roadway, so that this section of the curve has a coefficient of friction that is less than the original one. What is the maximum safe speed to make this turn is v1. Mark the correct relationship between the original speed and this new speed on the wet surface. Well, to be able to answer this, we have to recognize that the acceleration that we have to provide is related to v squared over r. And the friction that needs to supply that acceleration is limited by mu sub s times n. If the coefficient of friction is going down, that means that maximum friction force is also going down, which means that the acceleration, centripetal acceleration maximum, is also going down, which means what about the velocity? Well, the velocity makes up the centripetal acceleration in the square of it. So obviously, if this acceleration is going, the maximum acceleration is going down, that maximum velocity is going down as well. So let's try to explain that in a way without kind of using all these equations. So we want to start with sort of our evidence, start with the things that we know. For instance, the friction force F provides the centripetal force. Okay, so that's what's providing that centripetal force, that inwardly towards the center of the circle directed force. If the coefficient of friction decreases, and obviously we want to refer to this n because it's related to that too, and the normal force remains constant, then there will be a smaller maximum frictional force. To provide centripetal acceleration. Okay, so those are some pretty clear statements of evidence. We've created a logical connection there. So let's go ahead and also link in this idea of the radius, because we know that the centripetal acceleration is also related to the radius. So if the radius remains constant, then the max speed v1 must be smaller. So this is our conclusion, must be smaller than v0. Suppose the police car arrives at another section of railway so that the curve that also curves but has a radius of curvature that's greater than r. The maximum, say, speed to make this turn is v2. And what's the relationship between v2 and that original? So we're assuming that we're back onto the dry roadway. How does the acceleration, that max speed, change if the radius is bigger? Well, if the radius is getting bigger, but the velocity is staying the same, then the acceleration would be going down. Remember, acceleration comes from our frictional force. Well, the frictional force isn't changing in this scenario. Okay, so we still have that maximum frictional force available to us. So if the radius is going down at the same speed, then the acceleration is going. If the radius is going up, the acceleration is going down. So to get back to the same acceleration, we can speed up. We're allowed to speed up to get back to that same maximum acceleration. So if radius goes up, the velocity can go up as well to keep the acceleration at the same. So that's probably a better way to say it. As radius goes up, the velocity can go up as well to keep the acceleration the same. So we're allowed to have a larger velocity. So we'll say something like with a larger radius. The car has a smaller centripetal acceleration with the same speed, or we could turn that around and just say simply, therefore, the car can go faster to have the same centripetal acceleration. So that's reasonably short. A lot of the same things that you said back in this one probably could be referred to down here as well, but may or may not be necessary depending on how the flow goes. All right, so now we want to get a little bit more quantitative. We want to derive an expression. Again, a derive always begins with reference to a formula we know, such as Newton's second law. So the sum of the forces in the radial direction has got to be equal to mass times that centripetal acceleration. So we could, describe what we're doing simply as we go along here. So what are the forces in the centripetal in the direction? Simply, so we would say something like the force of friction provides the radial forces, the radial force, and then we can start plugging in our knowns. So the force of friction is equal to mu times the normal force, and that has to be equal to the mass times the centripetal acceleration. We can see that the normal force is simply m times g. So again, at each step along the way, we're kind of describing what we're doing. And then I think the next step would be plugging in exactly what that centripetal acceleration is, the v squared over r. And then we can cancel the m's on both sides, so we get mu g times v squared over r. And then we have, again, a solution that is simply mu times r times g. So again, that's the maximum speed that the car can travel around that circle, because this is the maximum static frictional force. So we've worked quantitatively to this answer. We've described our step along the way. Every one of those is a well-defined step. I guess the only thing that I'm not consistent with is we described r. We plugged in r. That was one known that I haven't plugged in. R is the radius of our circle. So we want to connect this back to what we talked about in part 1, how your expression in part C supports what you said in part B. So if we want to remember, part BI is about a reduction in the mu, and we said that we need a reduction in the speed. So let's connect that, qualitative, quantitative connection. So a smaller mu under the radical, the square root sign, makes the right side smaller, so V must be smaller than before. So again, that matches exactly what we were saying before, that a smaller coefficient of friction means that I have a smaller maximum velocity. So we're relating this relationship, a smaller mu on the right side means that the V is smaller on the left. So it's a qualitative, quantitative connection. And then again, when we saw it before, we said that a larger radius means that we could go faster. So R is a larger R on the right side results in a larger V as well. There we go.